At present, the fight to reduce pollution and research to use energy in a smarter way are engaged, and because of its size, car industry must be a part of it. But how? By reducing car weight and optimizing its energy consumption. Nowadays, our ultra-monitored and connected cars are composed by complex networks of wires, which have an important impact on their mass. Thus, simplification of this network is one of the big steps forward, and can be achieved by the integration of maintenance-free sensors operating wirelessly and powered by their environment. ENHANCE project creates a multidisciplinary research consortium which goes from chemical engineering to electronic and mechanic design. The researchers and industrials of the ENHANCE team are working to develop a hybrid energy harvesting system capable of powering wireless sensors for the car of tomorrow. The development of hybrid energy harvester is of a special interest due to their ability to exploit different types of wasted energy in a car, as motor vibration and heat, or simply sunlight. PZT is commonly used in piezoelectric harvester. However, to reduce its environmental impact, it may be replaced by lead-free material. For this purpose, the optimization of different material synthesis and properties are studied. My name is Quentin Micard. As part of ENHANCE project in University of Catania and ITN-ENHANCE, my work aims to bring a methodology for bismuth ferrite thin film synthesis which is compatible with conventional industrial processes. Bismuth ferrite, or BFO, is a multiferroic material with a high Curie temperature, above 800 degrees. So, we expect to create a hybrid photopiezoelectric harvester with high performance for application in high temperature environment. Synthesis of doped and undoped BFO is obtained through emulsivity process in a hot wall reactor with a bimetallic source of precursor. Initial substrate were expensive single crystal of strontium titanate, but step by step, the process is optimized for cheap metallic foil or silicon-based substrates. Among BFO properties, improvement of piezoelectric characteristic is one of the most important. The maximum can be obtained along the 1-1-1 crystallographic orientation. Thus, controlling film orientation during the synthesis is a critical aspect. Doping of BFO films with rare earth elements will also help us to enhance piezoelectric and photoelectric properties by increasing coercive field, limiting leakage current, changing carrier concentration, mobility, and so on. At first, sample analysis we perform are focused on structural and compositional properties. Several techniques are used to do so. Structural properties are investigated through X-ray diffraction, Raman spectroscopy, and scanning electron microscopy. In the same time, X-ray photoelectron spectroscopy and energy dispersive X-ray spectroscopy are performed to control the chemistry of the thin film. Then, after optimization, piezoelectric properties of BFO are determined by D31, D33 resonator, and by PFM. Photovoltaic properties will be studied by illuminating a simple sandwich structure of the material. By gathering all this information, we aim to establish the relationships between processing, composition, structure, properties, and performance of BFO on cheap and easily available substrates. To conclude, I would like to thank the Professor Malandrino, the Professor Condorelli, and all the research team from University of Catania, and of course, all ENHANCE project partners and beneficiaries.